Welcome back to G-Fun Facts Online. Today we are unpacking a transformation that is arguably more significant than the Industrial Revolution. We are talking about symbiotic engineering. For the last 50 years, the relationship between a human and a machine has been strictly master and servant. You were the operator. The computer was the tool. It was a calculator, a drafting board, or a compiler, simply waiting for your input to execute a command. It was passive. Today, that dynamic has fundamentally inverted. We are entering an era where our tools talk back. They offer alternatives. They independently solve problems we have not even identified yet. This is not automation. Automation is when a machine mindlessly repeats a task to replace you. This is symbiosis. This is where human creativity and AI speed merge to create a collective intelligence that exceeds the sum of its parts. As we move through 2026, the engineer is no longer just a builder. They are becoming an orchestrator of synthetic intelligence. The archetype of the lone genius sketching on a napkin is dead. It is being replaced by the Centaur, a human-AI hybrid team. In this model, the human provides the intent, the ethics, and the creative spark, while the AI provides infinite scale, instant validation, and rapid iteration. Today we are going to explore the depths of this new discipline. We will examine how symbiotic engineering is reshaping industries from microchip design to bioarchitecture, and why the future belongs not to those who can code the fastest, but to those who can best dance with machines. To understand symbiotic engineering, we must first distinguish it from traditional automation. Automation is about removing the human from the loop to increase efficiency in repetitive tasks. Symbiosis is about keeping the human in the loop to increase complexity and quality in creative tasks. The core mechanic of this relationship is what we call the 70-30 protocol. In a symbiotic workflow, AI handles the heavy lifting. This is the 70% of engineering that involves data retrieval, compliance checking, basic code generation, and simulation. This liberates the human engineer to focus on the top 30%, which are the high-value tasks of conceptualization, ethical judgment, system architecture, and solving edge case problems. This shift allows for a phenomenon known as cognitive symbiosis. In this state, the friction between having an idea and testing it completely disappears. Imagine an engineer verbally describing a mechanical bracket. Within seconds, an AI agent generates 50 distinct 3D models. It runs stress tests on all of them, filters out the ones that are impossible to manufacture, and presents the top 3 candidates for human review. The human did not draw a single line, yet they engineered the solution by defining the constraints and the goal. Nowhere is this symbiosis more mature than in the realm of electrons and code. In the semiconductor industry, companies like NVIDIA are pioneering tools like Circuit VAE, a variational autoencoder that collaborates with human designers to optimize chip layouts. Designing a modern GPU involves placing billions of transistors, a task that exceeds unassisted human cognitive capacity. In the symbiotic model, the human designer sets the high-level goals, such as maximizing performance per watt for a specific logic block. The AI then explores a continuous latent space of design possibilities, generating thousands of layouts that a human would never consider. It does not just place components. It trades off power consumption against signal integrity and thermal dissipation in real time. Crucially, the AI is not just a black box. Platforms like CELUS are transforming circuit design by allowing engineers to describe a functional block. For example, an engineer might say, "I need a Bluetooth module that connects to this specific sensor suite." The AI automatically scouts the component supply chain, verifies stock availability, retrieves the datasheets, and generates the schematic connectivity. The engineer's role shifts from reading hundreds of PDF datasheets to evaluating the system-level architecture proposed by the AI. In software engineering, the concept of pair programming has evolved into AI copiloting. It is estimated that by late 2025, over 40% of new code is being generated by AI assistants. However, the most effective developers treat the AI not just as a code generator, but as a relentless sparring partner. They use the AI to write unit tests before the code exists, to refactor legacy codebases into modern languages, and to simulate security attacks against their own software. The human provides the why and the what. The AI provides the how. Moving from bits to atoms, symbiotic engineering is also revolutionizing how we manufacture physical objects. The automotive industry, which has traditionally been slow and risk-averse, has become a hotbed for this new discipline. Consider the wiring harness of a modern electric vehicle. This is the nervous system of the car, containing miles of copper wire and thousands of connection points. Traditionally, this was a nightmare of manual routing. Today, tools like Siemens Capital allow for generative design, where the human engineer defines the spatial constraints of the chassis and the electrical requirements. The AI then grows the wiring harness like a vine, finding the optimal path through the vehicle's body to minimize weight and interference. At BMW, this symbiosis extends to the factory floor. Quality control is no longer just about cameras looking for scratches. It involves vision language models that can reason about what they see. A human inspector works alongside an AI that does not just flag defects but suggests root causes. If the paint on a hood is too thin, I might cross-reference this with the humidity sensors in the spray booth from 3 hours ago and the specific batch of paint used. It then presents the human with a hypothesis, suggesting that viscosity was likely too low due to a humidity spike, and recommends adjusting the solvent ratio. The human validates the insight, and the process improves. We are also seeing the rise of digital twins as the ultimate symbiotic interface. In Formula One racing and aerospace, engineers no longer just look at telemetry data. They converse with a digital replica of the car or plane. An engineer can ask the digital twin what happens to the front wing aerodynamics if they increase the track temperature by 10 degrees. The AI runs a physics-accurate simulation and returns a visualization. This allows for counterfactual engineering, exploring paths not taken at zero physical cost. Perhaps the most profound application of symbiotic engineering is in biology, where the complexity of nature often overwhelms human intuition. Here, the AI acts as a cognitive microscope, seeing patterns in data that are invisible to us. A landmark example occurred at Imperial College London, where researchers partnered with a Google co-scientist AI to tackle antibiotic resistance. For a decade, human scientists struggled to understand how certain superbugs were sharing genetic material. The AI agent did not run a single wet lab experiment. Instead, it ingested decades of papers, data logs, and genetic sequences, eventually hallucinating a novel hypothesis involving viral shells as transport vectors. The human scientists, initially skeptical, designed a physical experiment to test this AI-generated hunch, and it worked. This is the essence of symbiotic engineering. The AI proposes the hypothesis, and the human provides the empirical validation. We see similar breakthroughs in materials science. Researchers are using large language models to mine millions of botanical papers to find bio-inspired engineering solutions. When a team needed a new type of reversible adhesive, their AI partner suggested looking at the microscopic structure of pollen grains, a connection no human specialist had made because the relevant papers were in completely different subfields. So how does an organization actually implement symbiotic engineering? It requires more than just buying a generic chatbot subscription. It demands a restructuring of workflows around the human-in-the-loop principle. First, the prompt becomes the design language. The ability to craft precise, context-rich prompts is now a core engineering skill. It is the new syntax. Engineers must learn to speak machine, breaking down complex system requirements into logical steps that an AI agent can execute without hallucinating. Second, the workflow must be based on iterative feedback loops. It follows a generate, evaluate, and refine cycle. The human sets parameters, and the AI generates 100 variations. The AI pre-filters these based on hard constraints like physics and cost. The human then evaluates the survivors based on soft constraints like aesthetics, user experience, and ethics. Finally, the human selects the best candidate and tweaks the parameters, causing the AI to regenerate a focused batch. Third, there is the glass box requirement. For symbiosis to work, trust is essential. Engineers cannot work with a black box that gives a magical answer without working. Symbiotic tools must be explainable. They must be able to show their work. If an engineer asks why a pipe was routed a certain way, I must be able to highlight the constraint, such as avoiding a specific heat source by 50 millimeters, that led to the decision. This brave new world is not without its perils. The most pressing technical challenge is the ownership gap. When an AI agent generates 70% of the code or design, who owns the result? If the bridge fails, is the engineer liable for not catching an error in the AI simulation? The consensus forming in 2026 is that the human is always the architect of record. The AI is a tool, however sophisticated. An engineer cannot blame the calculator for a wrong answer, and they cannot blame the AI for a structural failure. This increases, rather than decreases, the burden of responsibility on senior engineers to be master auditors of machine output. There is also the fear of de-skilling. If an AI solves all the differential equations, will the next generation of engineers forget the first principles of physics? There is a risk that we produce parameter tuners rather than true engineers. To combat this, universities are shifting their focus from rote calculation to systems thinking. The value of a human engineer is no longer in solving the equation, but in knowing which equation needs to be solved. Looking ahead to 2027 and beyond, symbiotic engineering will evolve into the agentic economy. We will move from chatting with a single AI bot to orchestrating swarms of specialized AI agents. Imagine a civil engineer designing a bridge. She will not just use CAD software. She will summon a team of agents. She will have a structural agent to calculate loads, a geotechnical agent to analyze the soil data, a cost agent to monitor the budget in real time, and a compliance agent that has memorized every local building code. These agents will debate each other. The cost agent might argue that a certain steel grade is too expensive, while the structural agent argues it is necessary for safety. The human engineer becomes the judge, weighing the trade-offs and making the final call. We are also moving toward generative reality in simulation. Engineers will soon walk through photorealistic, physics-accurate VR simulations of their designs that are generated in real time. A car designer could sit in a virtual prototype, drive it, and remark that the visibility over the hood is poor. I would instantly lower the hood geometry, adjust the engine placement to fit, and recalculate the aerodynamics, all while the designer is still driving. In the end, symbiotic engineering is not about replacing the human. It is about amplifying the human. It is a recognition that while machines are faster, stronger, and more precise, they lack the one thing that defines true engineering. They lack purpose. A machine can design a bridge that stands up for 1,000 years, but it cannot decide where that bridge should go to best serve a community. It cannot weigh the beauty of a skyline against the efficiency of a grid. It cannot feel the frustration of a user struggling with a poorly designed handle. The engineers of the future will not be measured by their ability to do what machines can do. They will be measured by their ability to dream what machines cannot. They will be the visionaries who harness the raw, chaotic speed of AI and channel it, through human wisdom and creativity, into a world that is not just more efficient, but more livable, more beautiful, and more human. This is the promise of symbiotic engineering. It is the merging of the silicon spark with the human soul to build a tomorrow that neither could achieve alone. Thanks for listening to G Fun Facts Online.